Right, good evening everybody and welcome to the April meeting of the BTS. This evening's event is the Harding Prize and we have 3 finalists. They have been chosen by the Harding Prize BTS subcommittee. We actually had 10 qualifying entries for this year's prize. The first presenter on my left here is Jake Rankin, is a data scientist, and his talk is on artificial intelligence for the forecasting tunneling progress. Jake gained a product design engineering Eng from Loughborough University in 2017, during which he worked for J.C. Bamford Excavators Limited as a design engineer. He recently completed a PhD in artificial intelligence for trench excavation at Loughborough University. During his studies, Jake worked for Murphy & Sons, where he used artificial intelligence to forecast tunnel productivity. He then worked at Havas Media and currently works for CGI, where he develops artificial intelligence tools and analytics for clients in a range of industries. Okay, all yours, Jake.
Good evening, everyone. My name is Jake Rankin, and I'm a computer scientist here to talk to you today about artificial intelligence. Now, before people get too terrified and think, oh, what is artificial intelligence? Is this more buzzwords from LinkedIn? I'm going to try and put some of your minds at rest and give you a quick run through on what artificial intelligence is. And we start by this magnificent field of AI itself, which is any algorithm that can be used for decision making. This can range from your spam filter on your emails all the way to your Siris and your chat GPTs. Within this, we start getting into machine learning. Now, machine learning are a series of algorithms that learn underlying representations from data and try to learn the underlying patterns from data. Within this, if we go a little bit deeper, we get into algorithms that use huge structures called neural networks, and this is going to be the body of the work that I would have done whilst at Murphy's. Breaking this down even further, we get 3 different fields of machine learning depending on what your needs are. If you are looking to try to predict what the fuel price is going to be or whether someone's wearing their PPE, you'll probably rely on supervised learning for your prediction and forecasting. Should you have any data that you wish to cluster, or if you have too much data that you wish to make a bit more concise, you would turn towards unsupervised learning. And finally, should you have any robotic excavation or you're looking to control factories, you would turn to reinforcement learning. Now, it may sound like it belongs in the realms of fantasy, but AI has actually already entered the construction industry. From looking at images and trying to understand whether someone's in a safe environment, to working with our good old friend BIM to make sure that teams are working more productively, ensuring that our suppliers are developing optimal logistics solutions, and, to my personal favourite, to robotic excavators to address the skill shortage gap. Now, this all sounds very interesting. Some of it might even sound a little bit niche, but the value in which AI is forecasted to bring into the construction industry is worth 1.8 billion for this year, which sounds quite big. And in 6 years' time, that number's going to get even bigger, looking at nearly 5 billion's worth in AI's value to the construction industry. Now, I was interested in trying to use AI in the tunnelling industry because forecasting tunnelling is difficult. I'm sure I don't need to remind any of you of that. And a lot of this difficulty stems from the tendering stage, where you have masses of data of all shapes and sizes that you're trying to process and understand. A huge source of this variation comes from your ground conditions, which can range from your sands to your clays to your silts to groundwater levels, and all of this variety impacts your machine. This raises complications on when should we get fuel in for our machine, when should we get the teeth changed, and when are we going to have severe breakages. And these are all problems that project management need to address. And all in all of this data is a bit of a headache for project management. And AI could be a solution to try to condense this information so that we have data-driven approaches. Now, I approached Murphy and Sons with this crazy thought of trying to put AI into tunneling. Now, unlike some of the other sections in construction, tunneling is relatively untouched when it comes to AI applications. Most of it is residing in the realms of academia, and there was a bit of uncertainty around this, and for good reason. We weren't too sure how well AI would actually do, or if it would be any good, leading to the main aim of the work that I'm presenting to you today, being to establish whether it is feasible to use artificial intelligence in the tunneling industry. And for that, we need some tools. And the tool I'm going to talk to you today are neural networks. And these are a type of machine learning algorithm that are inspired by the brain. They take in a series of inputs into something where they're summed up called a neuron, and they generate an output. All of these outputs are connected between each other to form the network, and all of these weights connecting each of these neurons undergoes changes during training. As you try to fit your output to the underlying pattern of your data, these weights begin to change. This all sounds very exciting. How do we go about actually establishing it? Well, first, with any AI-driven solution, you'll need some data. This can range from your humble Excel PowerPoint to handwritten documents to images and films of your work site. The data can be anything you can imagine. But the most critical stage, and the reason why so much AI solutions flop at the first hurdle, is because they don't undergo proper cleaning practices. If you're putting bad data into anything, you're going to get bad results out, AI included. This is the most essential part of the whole program. Once you've collected your data, the next stage is to select your model based on the problem. For our example, we're going to use neural networks because we're looking at trying to create a prediction. Once we have trained our model on this data, we are now ready to deploy our model into the real world where we can give it some new data and it can generate some outputs for us that can be of use. Now comes to the exciting part. I'm going to talk to you today about two case studies. The first is a historic cable tunnel, which was used as our feasibility scoping exercise. And the primary data set consisted of machine data, a bit of the tunnel data. And this was a potential application for machine performance. The second one, the North Bristol Relief Sewer, was using purely geological data only, no other machine inputs. And its application was to be in the pre-planning tendering stage or for forecasting how the rest of the build would go. Now, this historic cable tunnel was not an easy data set. It contains several parameters that we're trying to work with. We've got some horizontal alignment. We've got a bit of groundwater here, transitions from sand clay to chalk. And there was a bit of skepticism at this point, and we weren't sure how it would work. Oh, look at that. Here, we've got a graph that's predicting the machine's excavation time. And below here, we've got the average earth pressure balance of the machine. The green line on these is the training data that we use. The blue line is the prediction. The orange line is your actual real-world value. The error between these predictions is of an accuracy to 93%, and this is very, very close, considering that we're also capturing the spikes and the underlying behaviour of this excavation, even without as much data as one would hope to have at this stage. This was exciting. Murphy was very excited, and the construction industry has plenty of other challenges to go for. And this is where we put artificial intelligence to a proper test, and we started looking at the North Bristol Relief Sewer. And here we've got our wonderful machine. It's a EPB Lovett, and it's about 2.85 meters in a diameter. The North Bristol Release Sewer project is a tunnel that's about 5.5 kilometres long. At the time that I finished working on this project, it was about 3 kilometres in. The data set that we used for this was given to us by Maxwell, and these are probabilities of what's the likelihood of coming across different ground conditions. And this is where the challenges start. We were around here, and you can see there's some pink spikes here and this lovely spike of sandstone. We only have this data to actually train our model. Now, this is what we were expecting to see, and we had very little data on this sandstone. How is the machine going to behave when we're going to go through sandstone? We've also got some additional water around this stage. We've got some extra gypsum over here. We haven't really got much information at this stage to go on. On top of this, you do not give your machine all of this data. You need to keep at least a third of it away so that you can test that it's working. This makes it very challenging and means AI is going to have to learn the underlying behaviours of this ground if it's going to make good predictions. A further challenge to this as well, we have got some outliers. The aim of this project was to try and predict the ring cycle duration, and that's the whole process it takes to make one ring. We're talking from the muck to the excavation to the logistics for the total ring. And there's a lot of other data points that aren't captured, meaning we've got some big spikes in the data and we don't always know why that is. So how was AI performing? Well, on this little sample of data, bear in mind this neural network has never seen any of this blue data before. If you were a project manager and you were just given this orange line of the neural network's predictions, you would see you're going to be expecting some tough times around this stage. And as you come later towards your build on ring 3290-ish, things are going to get a bit calmer. And this can be very, very useful for trying to prepare how we're going to do maintenance, for example. But we're not stopping there. This is a small appetizer to what the real challenge was. We wanted to know when artificial intelligence thought we would finish this excavation by. So we fed in some data, churned a few cogs, and this is what the artificial intelligence would generate. Okay, so it thinks we're going to be having a bit of trouble here, a couple of spikes here. This might be the sandstone. And bear in mind as well, this was based on the average rings per week was around 63 rings per week at this stage. Now, this is where I would finish my predictions for Murphy. I submitted my results mid-October. The neural network was not touched again for the whole thing. Any new data that came in, we would have to see what this neural network would do. And I predicted a finish on mid-February. The neural network was within 10% of the final date. And this is considering that it's predicting that massive spike of sandstone that we have no information on, the huge spikes in gypsum, all the other uncertainties, and this is also considering that the data it was trained on had an average rings per week of 63 rings. What it actually was after that point had raised significantly to 111. The neural network had managed to actually capture that big jump in performance to predicting an average of 95 rings per week. And this was an exceptional performance, and because of the results of this, this generated enough excitement for Murphy to start undergoing the process of starting to bring a PhD student on board to try to deliver future work. We're looking at trying to make this more of a reality. And there are benefits to Murphy. We've got a model with very high predictive accuracy, and it's data-driven. We're not relying on as much guesswork. We're using the data that we've got, and we're compressing it down as something that's more manageable to help support project management in delivery. It was also shown to be able to capture the underlying behaviour and to be able to predict new data that it hadn't seen before. And this can be very important if you're at the start of a tender stage. It can be the difference of deciding to go for a project and deciding this is too much of a financial risk for us to continue. And you can look at the best and worst case scenarios. There's huge potential for Murphy, but also to the tunnelling industry. It's a benefit for all stakeholders as we can start having data-based decisions and start understanding where we might have problems and ensuring better planning. We can have huge access to future work. And as a little note as well, this was also a benefit to academia as well. This project that was done at Murphy is unique because prior to that, all of the research at that time had only looked at predicting data on a completed tunnel. There hadn't been any predictions on a live tunnel, so we're breaking ground into new researching territories. It was a pleasure to apply AI to tunnelling, and I'm grateful for the opportunity at Murphy. Thank you very much for listening.
Right, are there any questions for Jake, please?
Is this on? Yeah. Yep, I hope I'm not going to have to run around with this as well. Thanks very much, Jake. I've written several questions down, but I'll start with the one of your graphs had an obvious delay between what was really happening and what your AI model was predicting. Do you have a feel as to why that was happening?
So sometimes the error can source from many things, such as like breakdowns, for example, or different data sources. So that was one area that in future I would like to include, is to actually try to be able to log what the shift details are. It's not always easy to know what exactly caused that blip, and it's an opportunity to dig into it a bit further and to pull some more data from that out. But some of it was due to machine breakdowns and maintenance being longer than expected.
Thanks. And without listing every activity that we actually do you have a feel for where this might be where the AI might be extended to help us in other areas as well as just tunnel progress rates?
So within tunnelling, what you could do with it is, if you imagine the rails of your trolleys that are taking muck, you can use some sort of optimization algorithm to try to time the optimal number of trolley journeys that you need from the tunnel being filled to the outboard. You can use some of the metrics as well to actually control the machine. If you have data of the machine as well, you can look at predictive maintenance as well, which I think is an area that is very interesting. It's definitely applied a lot in things like automotive. And I think if I was doing something similar, I'd be very keen to look at how well it would do for predictive maintenance, because I think that could be very, very beneficial.
Thank you.
Yeah, Jake, very interesting lecture, Alistair Smith here. That model you presented was kind of based on a certain geological kind of profile. How much learning, if the geology changed kind of significantly, would be required? What sort of inputs?
So if it's so using the model that I had then, there'd probably need to be some data samples, but for future ones, so it's been about year and a half, maybe 2 years since I last looked at this. I think I would change my approach very rapidly. So what I'm planning to do in future, instead of having your individual ground conditions being inputted, I would have the actual breakdown of the soil property. So you can have your viscosity, your shears, your particle sizes, etc. And then you can start building models on that. What these networks are very good at is doing regression. So looking at taking a point from A to B and finding out the trend on that. If you were to have a new ground condition, what you could then do is input that, and based on the relationships it learns from your shears, your moisture contents, etc., you can start predicting new ground conditions you've never seen before.
Question right at the back.
Does your model take into account the incentives
I didn't factor in the Euros of the World Cup, I'm afraid. So-
In other words, the bonus the men were getting for the number of rings built per ship.
I did. I'm sure that will be a very interesting area to experiment.
The other thing I would point out is there are probably several contractors in this room that would be begging you to go working for the client. Because if the client had a few more rational ideas about how long a job was going to take, yeah, it would make life a lot easier for contractors. And the last thing I'll point out is an observation. There are a lot of grey-haired people that have been in this room and are in this room that can, from that grey hair, predict pretty much what you're saying. The problem with it is that if you include it in a tender, you won't win the job.
Yeah. So with my point on that, what you can have these models for, like, I would probably be the last person to fully put in my faith in an AI model. At the end of the day, like everything, it's a tool to aid with decision making and providing assurance. So if a more experienced tunneling person had a feeling that the ground conditions were going to be particularly tricky and the model shows something similar, that can help give them the confidence. I can't quite remember what your first point was. I've forgotten that bit, I'm afraid.
Oh, the men in the bonus.
Yeah, I think it was about contractors or something like that. But yeah, like the AI is very good, but I think it would take a lot of work to work on that aspect of the contract discussions with other parties, etc. It's a different model, but one I'd be interested in looking at.
One more question at the front, and then we'll move on.
Thank you. Thank you, Jake, for the really brilliant presentation. George here from the young members. Just a quick one. Early on, you tapped into the importance of being able to have a clean data set to work with, and I assume that for a data analyst to clean and filter out the proper data is quite a challenge. So any experience we'd like to share on how this from the working side, how this data could be better collected and maintained in order to be useful?
So in terms of like when you're getting your data together to begin with versus the data you already have, if there's data already there could be something you can still do with it. In terms of like the cleaning, you'd have to do things like dropping like NA values and stuff like that, and if there's any outliers, you would talk to people and understand why that is before dropping them. If we're going into a new project where we're starting from zero and we're thinking, right, we want to do a data-driven approach, we want to have various sensors established, etc., those sorts of conversations can be done. It's not always certain what sensors you would always need at the time, and indeed some of the projects you would start collecting data and realise there's an additional variable that I'll need to collect. But like the data collection bit is a very I think subjective discussion is one word, but it's doable.
Thank you.
Okay. Right, we will move on. Thank you very much, Jake, for that presentation. We will move on to our second presenter. Our second presenter is Ricardo Manis. He's a senior mechanical engineer for Riverlink CJV. It's a JV between Ferrovial Construction UK, BAM Nuttall, and SK Ecoplant. His presentation is on the pressure ring launch system at the Silvertown Tunnel. He's been with Ferrovial UK for 6 years, starting as a shift mechanical engineer in the Northern Line extension, helping with the assembly, launching and dismantling of both TBMs. Ricardo then spent 4 years at Tideway, where he was promoted to Deputy Plant Manager in charge of mechanical assemblies in Tideway Central, delivering the secondary lining works at Kirtling Street. When the major works in the tunnels came to an end At Tideway, he joined the Silvertown project, assisting with the assembly of the TBM and executing the launch of the tunnel, and is currently involved in the rotation of the TBM and its relaunch. Okay, all yours, Khaled.
Good evening, everybody. My name is Ricardo Manías. I am a mechanical engineer working for ferrovial construction at the Silvertown Tunnel project, and I will speak tonight about the system we use to launch our TBM. So our agenda for tonight will be a quick introduction of the tunnel, speaking also about the reasons we had to adopt the method we have used and we are currently using. Then I'll move on to the description of the structure involved during the operation, the operation itself, following for the disassembly of the launching structures, and finalizing with some conclusions and the lessons we took after our first launch. So the Silvertown Tunnel project will be a 1.4-kilometer twin-lane tunnel that will be constructed with the intention to relieve the traffic congestions and to reduce the pollution around the Blackwall Tunnel, and also to give opportunities to cross the river by using public transport with new passage routes. So this tunnel will have an internal diameter of 10.8 meters with 400 mil thickness segmental lining. The tunnel is getting constructed by using an earth pressure balance mode tunnel boring machine with 11.9 meter excavation diameter, which actually is the largest TBM ever built in the UK. So to understand why we choose, or why it was chosen this methodology, I gathered 3 reasons. The solution worked for compact shaft. So due to the space constraints in the launching chamber at Silvertown, or in Silvertown, and particularly the rotation chamber in Greenwich, those shafts had to be constructed to the minimum size required to assemble the TBM and the launching structure. Therefore, a more conventional type of launch would have been a real challenge to fit them in. Also, this system was valid to be reused for both shafts, and the structures could have had been restated also for the second launch. And after the first launch, we were able to achieve the learning curve, so that was also quite decisive. The construction of an adit to allocate partially the TBM got dismissed because the complexity of this work due to the shallow and difficult ground conditions around the areas. Now I will briefly explain the 4 structures that got involved during this operation. What you can see on the screen is what we call the shutter can. It's basically a circular structure that got embedded into the concrete head wall and acted as support for the following structures. So, after the assembly of this one, we were able to scan, to survey the TBM when it was getting constructed, to understand the clearances we were going to have between the sill and the tunnel eye before we were pushing the TBM against the wall. The second structure is also a circular one. It's the sill can that was connected to the previous one, and its main feature was to isolate the TBM, the sill, and the primary lining from any potential ingress of water, thanks to the 2 rows of rubber that were installed in the internal perimeter of the structure. That made fully contact with the sill and the ring during the first stages of the excavation. This big framework is the thrust frame and was capable to receive the imposed loads required to move the TBM, and also to transfer those loads into the slab and ultimately to the ground. The last structure is the steel ring. It was a circular structure of about 100 tons of steel. That piece was loaded by means of an external source, which in our case were four groups of cylinders connected at the back of the steel ring, and that one was able to transfer that load to the skeleton of the TBM and the thrust frame simultaneously. The way we loaded or the way the thrust frame was loaded was by means of those steel bars that were connected across both structures between the steel ring and the thrust frame. So the cylinders installed at the back were able to tension them. Despite this structure being pretty much a circular structure, was not symmetrical or completely symmetrical due to its working condition. It was expected to push harder at the bottom of the ring because the weight of the machine, and also to try and keep the verticality, the vertical offset of the TBN when this one was getting buried into the ground. So the bottom half of the ring was better reinforced for that reason. Also, as you can see, at the bottom of the ring, or at the bottom quarter of the ring, there was a void created in purpose due to the launching sequence. So as the machine was progressing, was moving forward, we had to install those rails, okay, for the TBM, or for the backup countries to roll over them. Okay. It's important to understand the interference or the interface, between when we were constructing the shaft between both teams, the tunnel team and the civil team. So they work together in order to place and locate the foundations, those columns and the base slabs in the right spot. For instance, we use this kind of templates. So we minimize any potential error that we might encounter in the future when we were installing the structure above the slab level. That slab had to be constructed with a 4% gradient downhill, as well as the upright structures, the head wall, that had to be perpendicular to the alignment due to the nature of the tunnel. Moving on to the operation of the system, as I said earlier, both structures were connected thanks to the DB ducts that were tied at both sides of the structure. So those cylinders were capable to load them. So it's very simple to understand how this system worked. Basically, there was what I call a rear lock nut tightened to the back of the cylinder. So as the machine was starting the excavation and marking out, the cylinder started extending until reaching the final stroke, which in our case was around 200 millimeters. After that, we had to tighten the inner lock nut inside of the stool against the steel ring to keep the tension of the bar, so we were capable to retract the cylinders and then move forward the nut. After all the cylinders were reset, we were able to resume the excavation with a new cycle. We need to know that all the functions of the TBM were enabled by the thrust system for obvious reasons. So when the conditions were sound to excavate, it was up to the TBM driver and the hydraulic power unit operator to agree when to resume this operation. In the table, that table is just showing as a reference the amount of strokes we had to achieve in order to cover the total distance of the launching and the speed rates of the power unit. I'm saying it's a reference because we were not able to match those figures. Basically, because not all the cylinders could extend at the same time. We had planned downtimes, as I said before. We had to stop for the extension of the rails and the conveyor structure at the back of the TBM, and also we suffered a few of unplanned downtimes that I'll explain in the following slides. Despite what I'm saying, the team managed to cut by 2 days the original program. Okay, this operation was monitored and controlled by providing real data or real-time data to both the TBN operator and the hydraulic power unit operator to see in a quick look the excavation parameters, so the thrust, the total thrust force, the stroke of the cylinders, and the advance of the TBM. Thanks to 4 draw wire sensors installed on the corners of the ring, we were managing, or they were managed to see the advance of the TBM and as well as to understand the squareness of the ring and try to correct it in case of any discrepancy. Also, the first concrete ring that was previously built inside of the teleskin was surveyed at every shift for the same reason, to understand if there were any kind of deviation or deformation of the ring. As for the parameters for the excavation, it was decided to split this advance into 3 different scenarios upon the different ground conditions the TBM was going to encounter. So we could assess better the expected thrust due to the friction and the increasing of the APB. For instance, in the first stage, when the machine was excavating through the head wall and the second piles, it was expected a thrust force up to 9,000 kilonewtons. In the second stage, when the machine was already in soft ground, up to 19,000 kilonewtons, finalizing with a maximum total force expected between 25,000 kilonewtons and EPB between 0.5 1 bars at the ground. As I said before, we had a couple of incidents. So as you can see in this top line, okay, showing the total thrust force for the machine to move forward. So that was increasing with advance, and also particularly you can see how that jump up to 24,000 kilonewtons when we started putting pressure in front of the cutter head. So at that highlighted moment, we heard a loud noise and we decided to stop and assess the situation. So we found out that the bottom joint of the steel ring was slightly deformed. We decided to park and call for a meeting with the designer. And after our proposal for the remedial works got approved and put in place, we were able to resume this operation 24 hours later. Another minor incident happened near the completion of the work. So the gasket of the key segment was not doing fully contact with the steel ring, and as soon as that joint passed through the in-by seal of the seal can, the water found a pathway into the seal. So we just basically inject an expansive foam to close the gap. The good thing is that we didn't observe any pressure losses, we didn't have any major delays, and it was proof that the seal can isolate successfully. After the completion of the launching, we had to, both structure, the steel ring and the thrust frame, were locked and left in position to give enough support for the TBN to keep advancing, basically for 2 reasons. We didn't have enough room at the back of the TBM to complete the full assembly of the machine, and also because there was not enough friction between the ground and the lining in order to overcome the required thrust for the machine to move forward. So after 45 rings installed in the tunnel, it was decided to stop. At that point, we should have theoretically around 100,000 kilonewtons that were, as a figure, much higher than the required force to move the TBN at that time was around 50,000 kilonewtons. So when we parked the TBM, we were able to dismantling the launching structures and to reconfigure the pit bottom for, to improve the logistics of the tunnel. So the operation for dismantling those structures was not without a challenge, since at that moment our crane capacity was much lower than the one we had originally during the assembly of the TBM. We had to rethink, restudy how to dismantle and strip down those structures into singular and smaller pieces, but without damaging them, since they had to be reused and transported across the river, at the other side of the river, and getting ready for the relaunch in Greenwich. Before I move on to the conclusions, I just would like to mention the notes or the lessons we took over Greenwich for the relaunch. Firstly, we had to redesign a couple of the structures. For obvious reason, the shutter gun that got embedded in the concrete portal was fabricated again, but this time was a bit narrower, just with enough width for the cutter head to spin inside. Also, the steel ring got, among other reasons, more reinforced. Basically because the incident we had, and also that void that I mentioned originally, or at the beginning of the presentation, that void left at the bottom of the ring was filled with a new panel that gave complete circularity to the bottom of the ring. Because now the launching sequence is slightly different, so those countries doesn't require or they don't require for the countries or for the rails to move over them. As for the operation, we have put in motion, we have implemented a more intuitive display for the operators to understand better the operation or to read better those parameters. We swap the draw wire sensors for laser distanceometers that will give us a more accuracy measure of the advance of the TBM, and also because they were giving us sometimes bad readings, especially when raining. And also the data collection, now it will be retrieved every 5 seconds. So just to conclude with this presentation, I wanted to say that the solution or this methodology that was adopted and approved by the CJB, along with the technical office, the designer, and the client, has been proved to be well assessed. A wrong methodology would have caused significant delays in the program and cost. And also, I want to say that this solution was successfully achieved thanks overall to the well execution operation, but by the delivery team and the subcontractors that understood perfectly this methodology. Thank you.
Right, thank you very much, Ricardo. Have we got any questions, please?
Yeah, I'll start it all again.
Okay. Cheers,
Thanks very much, Ricardo. That was a very good presentation. The over-stress and the buckling of the steel frame that happened, did you resolve why that happened? Was it something to do with the ground, or just keeping the TBM level, or friction? Or
Yeah. So, yes, we kind of understood why this happened. Okay, basically, we have two hypotheses. Okay, and the first one is related that that structure was not capable to receive, let's say, eccentric loads left to right. So we had to more or less push quite symmetrically, and also during the launching, one of the thrust cylinders at the very bottom of the ring was faulty, so that cylinder was not supporting that area of the steel ring, and we were thinking that that lack of support also helped for that joint to somehow displace or moved, and those were the reasons that why we think that damage happened, because after we did the remedial works, and we reinforced a bit better that joint, even the thrust force was increased a bit further up. But yes, those are the two hypotheses that we were managing, and we were managing those eccentric laws.
Thank you, Ricardo. Again, very interesting presentation. With the small jacks, you talked about lock nuts and doing that up. That process, do you think that kind of gave you any problems? Did you have any issues with kind of the manual input,
No,
shall we say?
No.
Okay.
Yeah. So.
Second question. Would you do it again?
Yes, indeed, I will say so, yes. I mean, do you mean the methodology itself, or the way how we manage
the methodology? Would that be now a go-to process for launching a similar TBM?
I think I will go for an easier way to launch the TBM. As I said, the solution was used because it was the better solution, or the best solution to put in place, particularly because we had this lack of space. We were handling massive structures because the size of the TBM and the space of the sub was quite tight. So that's why. I think that is the main reason why this solution was adopted. If I would do that in the future, I would say I will only do that if I'm somehow forced to do it. Okay, I think a more easy or an easier solution, it is going to give you the same results. Okay, to launch a TBM. So.
No, thank you very much. That's.
Any other questions? Another one from Mike.
Yeah, another one from Mike. Sorry, Ricardo. I've used this system once on a project, and that was launching on a straight, which looked like what you were doing here. Is that correct? You were launching on a straight rather than on a curve.
Well, we were launching on a straight basically because the TBM was built on top of a cradle, so we only could go straight. So. Do
you see any problems with actually launching on a curve? Other than the usual problems we have launching on a curve, that is?
There is always problem launching a curve if you don't have the proper alignment or the proper transition. The thing is, the tunnel started on a curve. Actually, if you see the launching chamber, it's already built on a curve. Okay, but you cannot build the TBM on a curve. So we are expecting this kind of deviation at the beginning of at the entrance of the tunnel that we had to correct in the first meters of the excavation. But if the question is that if we had any problems launching this TBM on a curve, no, not at all.
Any other questions before we move on? Okay, right, we will move on then. Thank you very much, Ricardo. We'll move on to our third presenter. Our third one is Dr. Agustin Lopez. He's a research associate at Imperial College London, and his talk is on new insights in the structural behaviour of grey cast iron linings. After completing his bachelor degree in civil engineering in Madrid, he came to the UK and completed an MSc at Swansea University in computer modelling techniques applied to engineering. He then joined Rockfield Global, working on geomechanics solutions for the oil and gas industry. After 3 years in the industry, he joined Imperial College to undertake his PhD studies in the development of advanced numerical models for grey cast iron tunnel linings. After completing his PhD in 2022, he continued working as a postgraduate researcher on the thermal analysis of the heat of hydration generated by newly constructed piles, on tunnel-to-tunnel interaction problems, and on the application of machine learning techniques in geotechnical engineering. Over to yourself.
Many thanks for the introduction, and I would like to start thanking the BTS for inviting me and for considering me for this award. So the title of my presentation is New Insights into the Structural Behavior of Grey Cast Iron Tunnel Linings, and it aims to summarize some of the findings from my PhD research on the development of advanced numerical models for cast iron tunnel linings. As you see, this research was conducted at Imperial College London. So, as you know, we have inherited hundreds of kilometers of tunnels constructed with cast iron tunnel linings, and even though this typology of structure is no longer adopted for new construction, they are still relevant from an engineering perspective because of the fact that existing tunnels are frequently affected by construction works taking place in the vicinity, and in those instances we need to perform structural assessments to ensure that the serviceability of the existing tunnels won't be negatively affected. So in this sense, it's worth talking about structural assessment. It's useful to know that these tunnels are, as you see on the picture in the right, are segmental, so they have structural joints which in their case are bolted connections, and the behavior of these connections is not obvious, and the effect of these connections on the overall response is not obvious either. So therefore, there is a need for assessing the ability of current analysis method for the analysis of these structures, and in particular for the way that these analysis methods take into account the presence of the joints. So in the paper I submitted, I considered two different questions. The first is, what is the influence of longitudinal joints on the response of segmental cast iron tunnels, and in terms of their analysis, whether we should be treating them as rigid or flexible structures. And in the process of answering this question, I'll introduce an alternative to these two methods. And the second question is, what is the stiffness of bolted tunnel joints, and what is the role of the bolts in the behavior of the joint? So the second question I'll very briefly touch upon, and I will be focusing mostly on this first question. It's useful to consider some of the terms that I'll be using later on. So I'll be considering only the analysis of a single ring, and in this sense, whenever I refer to joints, I'll be referring to longitudinal joints, which, as you've seen in the image, they are the ones connecting segments of a single ring. And it's also useful to know that crown, invert, and spring length, as you know, are the usual terms for denoting the different locations around the ring. In terms of side convention, positive bending moments will be those generating tension at the intrados, and also opening of the joints at the intrados, whereas the opposed bending mode will be taken as negative bending. I'll be referring to squatting and tunnel squat. So squatting is the typical deformation mode that we observed in tunnels of the London Underground network, where there is an enlargement of the horizontal diameter while the vertical diameter has reduced. And I'll be expressing the tunnel squatting percentage as the ratio between the increase in the horizontal diameter divided by the diameter of a circular tunnel. So the background of my research can be placed in an earlier experimental investigation that was mostly carried out by Jessica Yu during her PhD studies, also at Imperial College, and where she, using the setup that you see in this photograph, conducted an experimental investigation on a half-scale grey cast iron ring. And this work not only provided new insights into the behavior of these structures, but it also provided a wealth of data from which I could validate my different numerical methodologies in detail. So regarding this validation, the details about it can be found in the reference that I have at the top of the slide. The numerical analysis were carried out with the software ICFEP. And as you can see, the modeling strategy was to simulate the behavior of the ring with a 3D model that included, that aimed to represent accurately the geometry of the segments and the flanges. So things like the ball holes, the different components of the voltage system, and the caulking groove were all included explicitly. And also, the presence of interface elements at the contact between the segments enabled for the joint opening for the opening of the joints and the stiffness reduction associated to it to be simulated. So this model was essentially the basis of the results that I'll be showing later on. So now moving on to the actual methodology. So the numerical model was basically framed within the elastic continuum model, which is a well-known analytical solution for the tunnel lining forces and displacements. And this solution, among other assumptions, assumes that the tunnel lining is continuous, that is, it neglects the presence of the joints, which in the case of segmental tunnels, and in particular grey cast iron tunnels, is usually addressed by either adopting a rigid ring approach, where we adopt the full bending stiffness of the cross-section, or a flexible ring approach, where we apply some reduction factor to that bending stiffness. So in the case of this latter approach, the reduction factor that is usually applied in the case of cast iron tunnels comes from the well-known work by Muirwood in 1975. And I have the expression here. So eta essentially depends on the number of joints per ring, so it can be regarded as an empirical reduction factor. So I'll be later on comparing my numerical results against these two approaches, the rigid ring and the flexible ring. Regarding the geometry that was used in this study, it comes from the 11 feet 8 1/4 inch tunnel, which can be regarded as the standard size for running tunnels in the London network, and in particular this geometry comes directly from that of the central line. So as you see in the left, we have a joint located at the crown and a joint located at 60 degrees from the crown, and we only consider 1/4 of the ring due to symmetry considerations. And also on the right, you find the geometry and dimensions of the longitudinal joint for this tunnel size. So regarding the setup of the numerical model, it aimed to replicate the assumptions involved in the elastic continuum model. Soil stresses were applied directly on the tunnel stratus, and tunnel depths of 10, 20, and 30 meters were considered. The reaction of the soil was simulated via normal and shear springs also acting all around the ring. And two different interface conditions were considered between the tunnel and the soil. First, full bond conditions, where there is no slip allowed at the interface, and there is transfer of shear stresses across that interface, and slip conditions where there is relative displacement is allowed at the interface and no shear stresses are transmitted across. It's also worth noting that, as you see in the left, the ratio between the total horizontal and the total vertical stresses was taken as 0.7, as this enabled for the tunnel squat to deform into the squatting mode, which, as I mentioned before, is the standard of the typical deformation mode that these tunnels deform into. And lastly, stiffnesses Kn and Ks, which are the stiffness of the springs, were varied parametrically in order to investigate the effect of the influence of the joints at different squatting levels. So here are the set of results corresponding to full bond conditions. Note that those the results from slip conditions typically were essentially qualitatively similar to this. And here we have, from left to right, we have the results corresponding to 10, 20, and 30 meter depth. We have the solid line here corresponds to the analytical result using the full bending stiffness. The dashed line corresponds to the analytical solution adopting Muirwood's reduction factor. And then the broken lines with markers are the numerical results. So on the vertical axis, we have the maximum bending moments, which take place at the crown and spring line, and on the horizontal axis, we have tunnel squat. So one of the main takeaways here is the fact that between 0.5 and 1%, which is the usual range of squatting that these tunnels deform into according to field measurements, we have significant stiffness reduction. And this can be clearly observed at the deviation with respect to that solid line.
It's also, it can be observed as well the influence of the tunnel depth on the results. The point of deviation from that solid line is delayed as we increase the tunnel depth. And this is due to the fact that the stiffness of the joints is dependent on the axial compression, which is obviously larger the deeper the tunnel. It's also worth noting that at the spring line, which is very clearly observed in all cases, the bending moments are larger than at the crown, and so is the stiffness at those locations. And this can be explained by the fact that, as we see at the top, we have a joint at the crown location, and that joint, as you will see in a minute, turns out to be the one showing the largest opening. So the section at the spring line, being farthest away from the crown, is less affected by that joint opening. And finally, it's also worth noting that in comparison with the dashed line, remember that corresponds to the results from using Muirwood's reduction factor, we are always, even in the softest case, which would be the 10-meter tunnel depth and at the crown, the bending moments are always larger than those predicted by that factor, which indicates that when applying this factor and assessing internal forces, we can result in non-conservative results. In terms of the joint opening, these are the same results, but expressed in terms of the joint opening against tunnel squat. So clearly we observe that, as I mentioned before, the 0-degree joint opening, the crown joint is opening more than the 60-degree joint opening. And we also observe that in the three cases, and this again reinforces my previous comment of why the crown shows a softer response. And we also very clearly observe the effect of the tunnel depth on the behavior of the tunnel, so the behavior of the joint specifically. So as we increase the tunnel depth, the joint opening reduces. This is very evident for the 60-degree joint opening, with the associated increase in stiffness for deeper tunnels. So I've mentioned that adopting Muirwood's reduction factor can result in non-conservative results, but also using the full bending stiffness can result in overly conservative results. So I'm proposing a third approach here, where we adopt a flexible ring approach, but in this case replacing Muirwood's factor by a new set of bending stiffness reduction factors that are derived from my numerical results. So based on the fact that the stiffness around the ring is not uniform, as we've seen between the comparison between the crown and the spring line, I propose three factors for each tunnel condition. So the first factor, the lower bound factor, would be obtained from the bending moments at the crown. Then we would have the upper bound factor, which would come from the bending moments at the spring line. And finally, we would have the global reduction factor, which is meant to be representative of the average stiffness reduction around the ring, which is obtained using the tunnel squat given by the numerical model and some rearrangement of the equations provided for the elastic continuum model. So if we apply these concepts to the parametric studies that I conducted, we end up with 6 charts that you see in this slide. Each of these charts correspond to a specific interface condition and tunnel depth. And we also know that for each tunnel condition, these 3 reduction factors depend and vary non-linearly with the tunnel squat. So the way these factors can be used in practice, based on a given tunnel condition, we would adopt one of these design charts, or we would interpolate between them. We can use the crown and the spring line factors, which are based on bending moments, to correct the bending moments given by some calculation method, which can be the elastic continuum model or other calculation method. whereas the global reduction factor can be more appropriate when we are dealing with displacements. Remember that is based on the displacements of the model, and it can be, for example, adequate when we are dealing with a typical situation of assessing the displacements of an existing tunnel, and we are using say a finite element solver that doesn't have the ability to include explicitly for these joints. We can apply, if we know the tunnel squat that the tunnel in question has deformed into, we can apply this global reduction factor there. So just some conclusions. The bending stiffness of the segmental ring reduced with tunnel ovalization due to joint opening. Deeper tunnels showed a stiffer response due to the higher compression acting at the joints. The stiffness degradation was more prominent near the crown than at the spring line. The segmental ring had a softer response than that predicted by a rigid ring, but it was stiffer than a flexible ring when using the reduction factor proposed by Muirwood. And based on these results, a new set of bending stiffness reduction factors was proposed. And as we observed, these are a function of the tunnel depth, the soil tunnel interface condition, the tunnel squat level, and the location around the ring. And they can be applicable in simple calculations as well as numerical analysis when we want to account for the presence of the joints. Lastly, I would like to acknowledge my co-workers, my PhD supervisors, Dr. Katerina Sampusi and Professor Jamie Standing, as well as Professor David Potts. Many thanks.
Right. Have we any questions, please? Right, we've got one up the back. Have we got a microphone or?
Okay, no problem, I can speak up. When analysing existing assets, we quite often produce a result. Thank you. We quite often produce a result that suggests the asset should have fallen down already. Clearly, self-evidently, it hasn't. Whilst being mildly amusing, this is actually a real problem because when we're trying to introduce new infrastructure close to existing, we quite often get discussions around whether the existing assets are capable of taking the new loads that are potentially going to be introduced. Quite often the discussion revolves around whether the model is actually accurately representing what's happening, whether boundary conditions are being simplified, whether there's inconvenient forces at play that we can't actually model, so we just ignore them and so forth. My question is, do you think the work that you've done actually provides for perhaps a more pragmatic analysis that would lead to less of these problems?
Yeah, that's a good question. I mean, I think my work provides a way forward if you are dealing with a model that doesn't have, which I think is, in most cases for commercial softwares, don't have the ability to account explicitly for the presence of the joints, and if they do, that relationship that is used by the software doesn't represent what the joint actually does. So I think in those situations, certainly the results basically based on a tunnel squat, whatever tunnel squat the model is given, can be, the lining forces, the bending moments could potentially be corrected with the factors that I propose here. I mean, obviously, the best way forward would be to have accurate models that, particularly for the joint behavior, that can be used in structural elements, which are typically adopted in geotechnical analysis, and to have adequate models that actually predict the behavior of the joint adequately, and that can be used in conjunction with a sophisticated geotechnical analysis. And in this sense, we have also done some research on this, and we have developed, based on the behavior of my 3D model, we have developed a new joint model that does capture the behavior of that joint, and that can be used in geotechnical analysis.
Okay. Any other questions?
Yeah, thank you, Agustin. Very interesting presentation. I'm intrigued about your joint model in the first place, because unfortunately we didn't see much about that, your finite element modeling. Could you, well, perhaps describe could you describe the joint model which you have used in some, say, in a minute? Material, what did you use for contact elements, how does the whole thing work, what's your cutoff criteria, what's your failure mode?
Right. I mean, just let me point out that the joint model that I just mentioned is not the joint model that I use in this presentation. So this, what I use in this presentation were interface elements in using a 3D model that with solid elements that represents accurately the geometry of the tunnel, whereas the joint model that I just mentioned is a model for structural elements, for beam elements in particular. So regarding this, what I use for this presentation, I use interface elements, just a standard formulation of them with constant stiffness. The stiffnesses of these interface elements were carefully calibrated during the validation phase when I simulated the tests that were carried out at Imperial College, and the results were in excellent agreement. So that was a very important aspect of the modeling. And regarding the failure criterion, it was a more Coulomb failure criterion that didn't allow tension to develop. So when the stress wanted to go into tension, basically the model realized zero stiffness.
Okay, thank you.
Any other questions? Mike?
Thanks for the question. I've forgotten what it was now. Right, the perennial debate we have is whether we should tighten the bolts or loosen the bolts. So what would you recommend? And as a second part of the question, would your answer be the same if it was a spheroidal graphite ion rather than grey ion lining?
So, sorry, can you repeat the second question?
Would your answer be the same if it was an SGI, spheroidal graphite ion, rather than grey ion?
If the factors would be the same.
Well, it's a different material.
Yeah. I mean, regarding the second question, I think really, in my experience, it is not so much the material that governs the response of these structures, it's more the presence of these joints. So while there is a lot of emphasis put in whether grey cast iron, its stiffness reduces non-linearly from the onset of loading, that's definitely true in tension, but it is really the opening of the joints that causes the greater stiffness reduction. So I think, I mean, obviously with SGI you would have a different stiffness presumably, but if it's not too different from that of grey cast iron, I think the conclusions would be similar, as long as the joint arrangement is the same as I'm considering here. You have still a joint at the crown, and well, that's the most important aspect. And sorry, the first question was?
The first question was answering whether we loosen the bolts or tighten them up.
That's a very difficult one to answer in general terms. I mean, in the paper, I didn't include it in the presentation today, but in the paper I show some results that I think are interesting in this sense, because they basically evaluate what is the bending moment and rotation relationship if you have bolts and if you don't have bolts. And what those results show, that would be in the scenario where you undo the bolts, is that the bending moment of opening is not affected by whether you have bolts or not. But what is affected is the fact that with bolts, you have the potential for fracture in the flange. I mean, it's going to happen at large rotations. It's not going to happen in serviceability conditions, but it may happen. Whereas if you don't have bolts, that can be completely ruled out. That's what the results show. And in terms of tightening the bolts, the results indicate that, again, tightening the bolts do not affect significantly the bending moment of opening. So really, if you are concerned, if you are trying to tighten the bolts to prevent joint opening, the numerical results show that that's not going to work. as the joint rotates more, and the positive bending moment, there is, again, no difference if you tighten the bolts or not, because on the positive bending, you don't have the three bolts working at once. You only have the outer bolts, and then the third bolt becomes active subsequently. So there is no big difference there. But under negative bending, if the joint is opening at the straddles, then the three bolts are active at the same time, and you see an increase in stiffness as you tighten the bolts. But if you are only concerned about opening, yeah, it really doesn't do much, from at least according to the numerical model.
Thank you.
Thank you. Any further questions? Okay, so we will move on then. Right, I think first off, a big thank you to our 3 finalists. What will happen now is our judges will leave and confer outside as to...
Is the bar open, yeah?
You're not going to be that long, hopefully. So they're going to confer and come back with their decisions in a couple of minutes. I understand they're talking about 5 to 10 minutes. In the meantime, we'll go through any of the business slides, and hopefully, if I take my time over there, the two will coincide and they will be on their way back. So, right. The first slide, which you all enjoy, is the drink sponsorship and the food sponsorship. The drink sponsorship is by Riverlink, and the food sponsorship is by Mappy. There is limits on both, so it is on a first-come, first-served basis. But I understand there is some flexibility in that as well. Okay. Next slide is 2 weeks on Friday, 2 weeks tomorrow, is our annual dinner. There are a few tables remaining, so if anybody hasn't booked a table, there is booking available through the website. Also, there is a deadline for any dietary requirements, which is the 20th, which is next Thursday. So please, anybody that's booked and is the key point of contact for the table, please ensure that you get your dietary requirements in for your table by then. It should be a very enjoyable evening, and we have, as our guest for the night, we have Kevin Keegan. So he is doing a presentation. So please fill up the last tables, that would be great. Future events. The next event is Thursday, the 20th of April. This is run by the young members, and it's on Euston Station LU Tunnels for HS2 Design and Construction, with a start time of 6 o'clock here in person at the ICE. The next slide is 25th of May, again by the young members, and this is a workshop, low carbon sprayed concrete, maximising the potential for carbon reduction. This is from 3:30 till 5:30, and it's in person again at the ICE. Registration is required, and this you can see through the website and through the mailing list and various other social links. The World Tunneling Congress is taking place between Friday the 12th to Thursday the 18th of May. There's a call for working group attendees. you can see the list of various working groups. So anybody that is planning to go to the World Tunnelling Congress in Athens, please contact the BTS. The email is there. It's just so that we can plan and work with the numbers and understand who's attending to which working group or the committee meetings. So anybody that's going, please let us know. That would be great. The next main meeting is Thursday the 25th of May. It's the AGM and the May meeting. It's on the North Bristol Relief Sewer Project. Please note that the start time is 6:30. That's down to other events being held in this room beforehand. We will have the short section of the AGM first, with the lecture starting at the latest at 6:45. Again, it's in person here at the ICE. Moving on to the June meeting, Thursday the 15th of June. Design of watertight structures. Can we rely on self-healing of cracks in concrete? That is back to the normal start time of 6 o'clock. Again, in person here at the ICE. The young members have a date in the diary for their conference of the 29th, Friday the 29th of September. There's a call for presenters. They'd like to get them in and so they can finalise their programme. And that will be from 9 o'clock in the morning till 6 o'clock, and it's in person. Information will be on the website. There's also a general call for papers about any project or research. Please email into the BTS if you've got any ideas or any other colleagues that could present. We're always looking for presenters for all our future meetings. And that also is the same for the young members. They're always looking for people to present as well. Moving on to the BTS Design and Construction course. Bookings are going well, but there's still plenty of time to book people onto that. So anybody that you know that will benefit from the 5-day course at Warwick, that's from the 3rd to the 7th of July. There is an early booking discount that will run out at the end of April. There are up to 5 sponsored places available. We've extended the application date to, again, the 30th of April. So if you know anybody that will comply with the requirements for the sponsored places, please encourage them to apply. The SEN inquiry for 2023, the BTS is looking for feedback on the proposed revisions of the 2 TBM safety standards. The draft standards and comments form can be found on the BTS website. It has to be completed as per the form. These need to be returned to Donald by the 20th of April, so that's again next Thursday. And if you were here last month, Donald was really emphasising that the form has to be absolutely complied with. And going forward, if you want to, those are all our various links. Please look up the BTS and again, come along to our future meetings. Right. Yeah, that's perfect timing. Right, and I'd like to announce that our judges have decided that Jake Rankin on artificial intelligence for forecasting tunnel progress is this year's winner. Right. Thank you all very much for your presentations, and we'll close the meeting at there, and we'll move on downstairs to the bar for sausage and chips and a pint. See you all down there.